This problem from section 2 is an interesting weave of more of the previous calculus experience we've had, and even pre-calculus. This one's talking about a projectile in motion, and the only thing tying into anything new here is maybe some notation, okay? So it says basically a projectile is fired straight up with an initial velocity of 100 meters per second, problem number 26, in the e-text, from the top of a building that is, should be 20 meters high. Okay, so 20 meters high. Okay, and what they have are several questions. They say, what's its maximum height above ground? At what time does it go past the top of the building? Because it's going to go up and come all the way down to the ground below the building. And then it says, how long is it flying in the air? So these are kind of typical problems. Now we got to assume we're on planet Earth at sea level. Okay, I think there's a problem here about planet X or planet Claire or whatever it might be, and they have a different gravitational constant. But the way it starts is, if you remember, let's do this in blue again. We start with an acceleration function, and it's a constant acceleration. There's nothing forcing it. There's no variable acceleration. The only acceleration that's happening, there is no booster rocket. It just fires, and the rest is gravity, and gravity is the acceleration heading towards the center of the Earth. There are two numbers they teach us in physics. One is meters, so it's like 9.8 or 9.81 meters per second squared. Or if you're working in feet, then it's 32 feet per second squared or something. We're going to use the minus 9.8 variety. Why? Because they're working in meters, okay? So here's where the other notation comes in. Another way to write that is to say x double prime, okay, is equal to negative 9.8. And folks, that's a differential equation. We didn't know we were dealing with it, but your teacher did, or he or she, when they're teaching you. That's a differential equation. Now to bump up to the other functions, the next function up is velocity. And that is x prime. And then after that is position, x of t. That's what he uses, and that's your x. It's the hierarchy of functions. X is your position. Okay, and x prime is velocity. And finally, x double prime is your acceleration. Okay, and all of this is just basically, okay, that's what's underlying everything, which is pretty cool. But what you do is you, of course, you integrate your acceleration, negative 9.8, and our live variable, in this case, is t for time. How long up, how long down, that kind of stuff. So we end up with a negative 9.8 t, and then you go plus some sort of constant c maybe. Oh no, it's one of those initial conditions again. But when you take this information up here, let's see if we can see this stuff. Okay, it says an initial velocity of 100 meters per second. What that means in our notation is v of 0, when you start the clock, is going upward 100. You might wonder, why did I make acceleration negative there? I'm thinking it's accelerating down is negative, up is positive. I know certain classes in physics, it's the reverse. This is negative, this is positive. Some teachers teach it that way. I'm not going to do the whole problem. I'm just going to set it up and show you. You guys probably know how to do this. I'll show you the A, B's, and C's for fun, but I'm not going to calculate anything, just show you. Another name for this they use is V sub 0, which is the initial, and that is your initial velocity. Well, when you plug in 0 for t here, you get 0, and it's supposed to equal 100. So what you discover is that c should be 100. So our work here is, oh, I'm not even going to show you that. This is actually negative 9.8 t, and then when you plug in 0, you should get 100 meters per second for velocity. So that's our velocity function. We're not done. Let's go one more step to integrate one more time. We're going to integrate negative 9.8 t plus 100 dt. And when we do that, we get the famous negative 4.9 t squared, okay, plus 100t, and then plus some other constant k maybe. And lo and behold, we also have an initial condition for our position because they told us that it launched off of a 20-meter high building. So what we know is x, right? 20 meters, x sub 0 is equal to x of 0. Another way of saying it is it starts 20 meters high. So that means when you plug in 0, this is 0, this is 0, and you get 20 there. So finally, what we have is our position function, classic Newtonian physics or whatever, motion problem. And what we have is a negative 4.9t squared plus 100t and then plus 20. And you can see, oh, that's the initial velocity. Oh, that's the initial position. It always falls out that way. You don't have any air resistance or anything like that. This is in a vacuum. And so the questions they ask are typically the max height, part A. The max height is it shoots up, and at just this moment, the velocity is 0 before it plummets back down to Earth. So the picture, here's your building, and this guy's going to fall to Earth like that. So right there at the max, the easiest way to deal with that guy is to simply go, oh, it's when you set velocity equal to 0. So you take your velocity function, which is negative 9.8t plus 100 equals 0, and you get the time that happens is when t is 100 divided by 9.8, which, you know, you might keep that in your calculator. And then what you would do is, oh, you want to know how high that went. Well, the max height then is equal to x of 100 over 9.8. And that is this fun function here, that inverted parabola. Another way to find it is use a derivative, right? You take, well, we did. We used the velocity, set it equal to 0. There you go. You could do, if you're in pre-calc, you go, oh, well, I'll find the vertex and I'll use the minus b over 2a or whatever to find it. But anyway, you can answer all these questions here. And I don't think I'm going to look at the others. You guys know this stuff. Just wanted to show you that this is in here, just to remind you. And the fun part to show you is, hey, look at, we're going to start going farther than we've done before. This chapter here just gives you a review of calculus and how it's nice to see woven into this the differential equation notation that goes with it. Okay, on to other stuff. We'll go to the next section, section 3 coming up.